Tough act to follow.
Leakage. Oh, I'm sorry. The next talk will be given by Chris Peikert, who will talk about pseudo-random functions and lattices.
Good. So this is joint work with Abhishek Banerjee at Georgia Tech and Alon Rosen at IDC. We're talking about pseudo-random functions. That's a family of functions where if you choose a function from the family at random, it looks just like a truly random function given Oracle access. And there are tons of applications in symmetric cryptography of these objects. So we know two theoretically sound way of generating or constructing these. The first is the seminal work of GGM, and its good thing is based on any pseudorandom generator, but unfortunately it's very sequential. So you have to run it k times iteratively to get for a k-bit input PRF. The other way of doing it is based on a series of works by Reingold and Rosen. And these are really nice. They're based on a semi-generic object called synthesizers or number theory objects, and they give you really low depth PRFs. So log squared depth, or even log depth, or even constant depth if you allow threshold gates. That's TC0. Downside is that to get these really low depths, you need huge circuits and mucho preprocessing. And the other problem is that there's no post-quantum construction using this kind of paradigm that we knew of up to this point under commonly accepted assumptions. So we're going to be addressing these things. So our results are that we have some low depth and relatively small circuit PRFs. And it comes from the LWE problem or the ring LWE problem, which is a special kind of lattice problem. And so we have two constructions. One is a synthesizer-based PRF. Just like Reingold, it's in NC2. And we have a direct construction, just like Reingold and NRR, and that's in NC1 or even in TC0. And our main technique, which is of independent interest, and people seem to be more excited about the technique than the result, which is fine with me, is a de-randomization of LWE, which allows you to, in effect, generate errors deterministically, which seems to be an important kind of necessary thing for solving this problem. So let me introduce the de-randomization technique. We call it learning with rounding, based on its connection to the learning with errors problem of Rega from 2005. If you know the learning with errors problem, it's basically to distinguish random linear products, random inner products with a secret S that have been perturbed by some noise from truly uniform pairs. Okay, so this little red EI is a tiny little error term. Okay, so the goal of the problem is to just determine whether you're being given pairs like this or pairs that are just uniformly random. And a new interpretation that we have of this is that, well, let's just see these little errors as sort of wiping out or kind of killing off the least significant bits of the inner product. Okay, so you take this inner product of A and S, and then you just kind of blur out the low order bits of it by adding error. So learning with rounding is something that we introduced, and here's a picture. So the idea is instead of adding error, you just look at, say, what bucket did the result land in. Okay, so we have 24, Q is 24 on the outside, and P is 3 on the inside. And so you take the inner product, and then you just output which bucket it landed in, 0, 1, 2, or 3, or 0, 1, or 2. And so the problem is to just distinguish pairs of this form, where instead of adding noise, you just wipe out the least significant digits and determine those from random inner products. Okay? So with that, we are able to prove that LWR is in fact as hard as LWE, which is good for appropriate parameters. You can see the paper for those. And I'll just flash up synthesizer-based PRF. If you don't know what a synthesizer is, that's what it is. But the PRF looks something like this. If you want, let's say, 128-bit input, then you have D equals 7. We have a chain of 8 moduli of decreasing size. And the secret key is a bunch of square matrices. If you think square matrices are too big, you can use ring elements from a certain polynomial ring. But here's what it looks like. You just kind of in a tree-like fashion combine these synthesizers in a tree going up. And based on the color scheme, it's a Christmas tree. So that's what the function is. If you want to do better, then you do something like this. It's a subset product function, which looks a lot like Reingold. You can evaluate this in TC0, see the ePrint. Thank you.